Okay, great. Well, hi, everyone. Thank you for staying to the end of the conference. Yeah, the first lightning talk actually is not on research, but on a new initiative that TLDR is doing for this year's conference, the 2025 TLDR Data Repository. I'm Tavas Gupta. I work at the SMG team at Consensus. And yeah, I'm excited to share what we've been working on the last few weeks. The goal of the 2025 TLDR data repository is to ensure that the data sets used in the empirical papers from the TLDR fellows are open source, reproducible, and easily accessible. And yeah, each repository will contain the schemas for the data sets used in the paper, some of the scripts to pull the data, and detailed instructions on how exactly to implement the data pipeline so that you can explore on your own or perhaps build on other authors' research. So I'm not going to do the links, so we can just stay in the deck, but I have some screenshots. This is the front end, the link that I'll share at the end. This is what it links to. And we have these papers hosted by Allium, so thank you very much to them. And yeah, for each paper, you can see that we have a link which has a version of the README. And then we have a Google Drive folder, which either shares the data set or in some cases a sample of the data set, and the GitHub link to the repository. Yeah, and then also at the top, there is a GitHub link to the parent repository. It's organized within submodules. So if you want to get some high-level information, you can go there. So for an example, actually look at Christoph's, who just gave the last talk. This is the parent repository, and all of the papers are located in the authors folder. So for Christoph's, we can see that there is the data folder, which contains some of the scripts to pull the earlier part of the pipeline, if you remember that diagram from his presentation. And then also for the two tracks of detecting the arbitrage opportunities and simulating the different paths, there's the folders there. So that contains the scripts. We can scroll down and look at one of the data output tables we can see here. So you have some sort of high-level variables on the metadata, the schemas, what it covers, the size, all of that, and then descriptions for each column, pretty basic stuff. But at the end, we have the implementation guidelines. So if you remember, that picture was in his talk, but it sort of goes in depth and explains how to actually execute each of these steps and where you can find those scripts. So if you want to look at the LVR for the cross-train arbitrage opportunities, this should be your starting point. And yes, as I said, we have those for the empirical works from the TLDR data fellows. You can find the front end page to access this at this QR code. The one thing I will say is that some of the authors and papers are still updating. So please keep in mind that things can change. But yeah, if with any questions, please feel free to reach out to me after the conference and or reach out to me on Twitter at that link. So yeah, thank you so much. Hopefully this is helpful, and hopefully it's something that we can build on in future iterations of the conference. Thanks.
Thanks for having me. I'm going to talk about Futarchy and Futarchy's fuel. Spoiler, the fuel is liquidity. Okay. So here's a way to represent Futarchy in a simple way. So what you want to optimize for is going to be typically a token price. So you can imagine on the left there, chart for the token price, and then when the Futarchy kicks in, you basically have a proposal that splits the token price into two kind of conditional cases, or kind of two superposition of states, if you want. And we're going to run prediction markets conditional on whether the proposal passes or whether it doesn't pass. And then, obviously, we pick the best version of the two. So that's the kind of essential way Futarchy works. What we're working on at Butter is conditional funding markets. And I need to run you through this quickly. So You take $1, split it into a funded or not funded case. So you get this proposal, do you want to fund it or not? And then you run 2 AMMs that are going to predict the DAO token price or whichever metric you want to optimize for using these pair of long-short tokens. So you end up essentially with 2 AMMs that we actually run as CPMMs. And you need to get traders to trade these markets. So you get information about which one of the two realities is the best. So to get this working, the intuition is essentially that you need liquidity. So liquidity is going to be there so as to have tighter spread. So basically you cancel out noise from those noise trades, but also importantly to elicit private information. So you want informed flow, and informed flow in that case is just like people who know things about the DAO, about the project that is undergoing this. So from that, you get more accurate prices, and thus you make better decisions. So I wanted to think, and that's kind of the thought experiment here, think about Futarchy as kind of an engine, and so you want to use liquidity as a fuel, and it has an efficiency curve, which I modeled quickly like this. So during the first phase, if you have little liquidity, essentially market is dominated by noise trades. So as you push liquidity up, essentially decisions are taken as random. So you just lose out on the liquidity that you put. So that you put in. So the efficiency goes down. And then when liquidity is high enough, you have enough informed traders with private info who want to come and make a profit out of their private info. So I modeled this as a simple, if I have private info, I am happy to just input it in the market so I get something out of it. A more complex model would be if I have innate utility, if I have opportunity cost, I can use this info in another way. So we could go much further than this. But here, basically, you end up on an increasing curve. And then once enough traders have already inputted their info in the price, then essentially then marginal returns are diminishing, which is the last mode. So yeah, that's just a way to think about how liquidity works and how it uses, how Futarchy works with liquidity. And so, yeah, it's a plug to think about how to make further research on the question, and the kind of thing we want to input in a model would be subsidy. So that would be basically an APR for LP incentives. What's the proposal impact size that affects efficiency, trader costs, so opportunity costs, transaction costs, and model for noise traders. Yeah, that's what we work on at Butter. If you want to learn more, you can scan this. Thanks for listening.
Hello, everyone. I'm super happy to be sharing this lightning talk with you as a fellow from this year. So a big thank you for all the organizers, Rafi and Beta, helping us over the year, and also my mentor, I think is not here, Pranav. So today I'm going to talk about my work, which is a very theoretical econ model on airdrops. I think the name kind of oversells it a little bit. And also I want to thank all the audiences who came up to me during the poster session, who reassured me that I could really shorten on the motivation part, because there's a lot of interest in better designing airdrops, which as you can see, shapes the network. So understanding the design and optimizing it will help the token projects to take off. So without further ado, we can go into the model setup. So very simply, to summarize, is a stylized two-stage model. And the timeline, very simply, you hear about the airdrop announcement, and we're going to model the responses from the users. And then we go back to the beginning to inform how the platform could anticipate the responses from the users and optimize the design of the announcement. So I'm not going to drop any mathematics in these 5 minutes. I'm just going to talk about the key parameters to let you know how simple and versatile this model can be for further modifications. So the control variable of this airdrop is going to be this decentralization beta. So it represents the share of governance tokens that will be distributed to airdrop claimants. And during this process, the response of the users are going to be dependent on the voting cost, like how sophisticated the platform is, how much technical difficulty or resources is going to be deployed in order to participate in the governance process, and how sensitive they are to the network effects. Because let's not lose sight for the fact that airdrop is mainly used for marketing tools. That means inherently it has some responses to the network size. The key assumptions I make for the kind of platform I'm designing this airdrop for is that I have heterogeneous users who have different abilities of enjoying the service on this platform that is going to guide them to make different using and voting decisions. Users are very sensitive or scaled by some parameters gamma to the network size, and they have a taste for decentralization, which is empirically proven to be true because the same platform are more successful as a decentralized organization in comparison to their counterparts as a centralized platform. And also agents are happier when they're surrounded by people around them. So we're going to have a very simple voting mechanism implemented in the model. And when they have people surrounding them who have similar alignment types, that's also going to affect their decisions in using. And the core trade-off, so after we have done the user side, we're gonna go back to the platform. The platform are gonna use beta basically as a bait to attract new users. The bigger the airdrop size, the more hype you create, you're probably gonna drive the adoption, but at the same time, you are gonna lose control of your platform. So the key results is we do have the empirically findings is consistent with the fact that we have a centralization results after the airdrop token becomes tradable. But another way to look at this situation is that the centralization is also filtering out the wrong crowds. You are retaining only the high alignment types to keep on be active on your platform. And so going more to the technical findings, basically from this very simple model, we are already able to draft out the design space for an airdrop. So we are able to inform the policymakers for some exogenous voting costs, depends on your platform. You should never do an airdrop, or what is the airdrops that are gonna be effective in driving adoptions. And also by using the explicit revenue function, we're able to plot out what is the improved revenue versus a no airdrop case. And this is just taking the slides from the 3D plot we had before. We have an interior solution to inform what will be the optimal airdrop designs. And all the future directions, I thank to all the audiences today, because I just wrote it before I come on stage. These are points we've talked about. So thank you guys for that.
Thank you. Hi, everyone. I'm Erwan. I'm the CTO at Penumbra Labs, and I'm going to talk about liquidity bootstrapping. And my goal is to lure you away from comfortable sinecures at prestigious universities to come eat glass with us in the arena. So first, about Penumbra, we're a private L1. It's an interchain shielded pool. It's a private DEX, and it works on proof of stake. The thesis of Penumbra is we're going to build a really good DEX. It's going to enable traders to find really good prices. It's going to bring in a lot of volume. It's going to enable market makers to quote really good prices. It's going to bring on more volume. And eventually, you yeet into orbit into a big shielded pool that everyone can use. The way the DEX works is by modeling each liquidity position as its own CFMM. this is a well-known, really good work from Guillermo Angeris, Alex Evans, and Tarun Chitra that basically lets you approximate any concave payoff using convex CFMs. The way the DEX works is by batching swap intents into those big chunks that are then piped into the DEX engine and routed against the entire liquidity graph. Liquidity providers can either be active or passive, or something in between where the protocol manages their liquidity for them. But critically, everyone has the same clearing price on their trades, and the protocol makes sure that there's an internal set of consistent prices by capturing the internal arbitrage and subtracting any economic artifacts from sequencing. Since all the trades are batched, you can decide to put trade 1 before trade 2 into the block, doesn't really matter. So fast forward a little bit later, you've built it, you're happy with yourself, but turns out you just stepped into the pain box, and now you have to actually launch it. And how are you going to launch it? Well, you can either go the dark way of self-dealing and private market making deals, and I guess now it's more frowned upon than it used to be, but you can also just choose to go the path of the light and design an open mechanism for anyone to subsidize price, so for anyone to participate and for the protocol to subsidize its own price discovery. And this is what we did. We built a liquidity tournament that is efficient at converting protocol cost rewards into liquidity that is transparent, that anyone can use, and that encourages wash trading. Wait, encourages wash trading? Erwan, what do you mean by this? Well, rewards are prorated to the volume that your positions are going to meter or earn. So your hit rate. Remember that trades are batched, that routing is global. So if you want to be a bad, big, mean wash trader, what you should do is commit inventory every block and quote really tight quotes. And turns out this is indistinguishable from being a really good market maker. So if you want to hear more about it, I'm around. You can also head to Twitter, where there's a blog post and a forum link where you can argue about whether this is incentive compatible or self-stabilizing, or if the mechanism could be made better. Thank you.
Hi, thank you so much. I'm thrilled to be here. This is so cool. I didn't expect it at all. Okay, so my name is Irene Aldridge. I teach in financial engineering at Cornell, and I also run a company, Able Blocks, because frankly, they don't pay me enough at Cornell, but it's a great financial engineering program if you're interested. Okay, so we are raising money for this product. So basically what we're trying to solve, and there's a paper, the link I'll post at the end. A lot of matching today is bilateral, right? So you have one-to-one matching, and it's kind of takes a really long time. And in many cases, you need to know what you want, right? So you have to talk to a financial advisor, or you have to run some quant model and determine like what do you want to buy, how much you want to buy. It's basically a pain. So instead, what I'm proposing is a multi-dimensional matching, and I'll show you that you can do it really, really fast. So there is a lot of literature recently on this topic, and most of it shows that to solve something like this, it's actually NP-complete, okay? So meaning you cannot solve it in polynomial time, and I'm going to try to convince you that you can solve it in O1. And that's what we're doing. So what we're looking is for the core, okay? So core in economics is an allocation that's a stable and it's irreducible set, and it's a very important part of game theory. And it's due to 1973 was a very popular time, but basically a classic example is it's some range of features or prices that makes the bargaining solution very, very stable. So what I'm doing is I'm basically using this framework, top trading cycles, that's been very popular, and I'm applying eigenvalue decomposition to the graph of the TTC, and with the latest improvements in eigenvalue speeds, you can actually solve it in O1, which means constant time, which means independent of how many features or products you have, you can solve it instantaneously. And you can apply it to cross chains, multi-preferences, multi-user decks. There's like a ton of applications. So this is just a simple example, right? So you have a bunch of objects, in this case 4, maybe 4 users as well. And in this TTC, you kind of draw the top preferences for everybody and you draw these cycles. That's why it's called top trading cycles. So it's a classic way to solve allocation problems from anything from housing to school choice. If anybody has kids in New York City, you probably heard about it. And so what we're doing is we're taking ordinal preferences, converting them to cardinal preferences. And then we're solving for steady state probabilities by applying eigenvalue decomposition. For example, SVD, which is my favorite. And we have all these proofs in the paper. And basically what turns out that the highest coefficient in the first eigenvector is your core. Okay, so that's the key result, is when you take this graph of all the different preferences and you take the eigenvalue, you take the first eigenvector, the top by absolute value coefficient in the first eigenvector becomes your core. And I have a bunch of theoretical results in the paper. It's a work in progress, so I'm sorry. I've heard it's sloppy, but you can also compute either you can sort it and compute different allocations if you really want to. So thank you so much, and it can be applied to many different applications. And thank you.
I'm here to present our design of a prediction market, constant product AMM, inspired by Uniswap v3. And first of all, just refresh on some of the concepts. So when we talk about prediction market, forecast contrast, event contrast, we were talking about binary options. And these are options that give you a predetermined payout as settlement. So when you spend 50 cents to get $1 to bet on a rating tomorrow, you're actually ascribing 50% probability. So, and of course, the sum of probabilities for calls and puts would add up to 1. And so when we set up the design, the prediction market AMM, we face a different set of challenges, of course, because we want everyone to be able to set up their own prediction market permissionlessly in one pool. They will be immediately able to trade 3 tokens, call tokens, put tokens, and the ERC20 collateral token. So essentially, you can use Uni token to bet on Doge prices if you want. But here, for simplicity, we are going to talk about stablecoins using as collateral. And for the settlement of the pool, we will use a decentralized oracle. And here in our AMM design, we use the same constant product formula as Uniswap v3. And main difference is that exchange price of this curve is the price of call and put tokens, and that is a cross rate. And we use the collateral reserves for these token call and put tokens for the curve. And to use a real-world analogy, essentially you will be swapping bagels to croissants on the Uniswap pool. That is a spot market, and a binary options pool like Divergence, you'll be swapping dollar amounts to dollar amounts. Which doesn't make sense, except that in an options market, every swapper is expected to exchange a collateral token to expected returns in collateral, so the payoff is delayed until settlement. And the other condition that makes this possible is that the expected return for a call token happens to be the value of a put token. So that's the put-call parity for binary options, which we combine into the constant product formula to make the 3 tokens exchangeable via a no arbitrage triangulation in math, of course. And the process would go from a collateral token delta to a price delta, and the delta of the options tokens that we would mint from the pool when the swap happens. And the constant product formula in this case will not only ensure that the collateral token and options tokens are swapped, but they also ensure the options are sufficiently collateralized. And in our case, the liquidity works in similar way to Uniswap v3, and basically the liquidity providers are the counterparties to the swappers. And they're passive sellers of call tokens and put tokens. And there are two liquidity types. One liquidity type is the collateral type. And in this form of liquidity provision, LPs would have to supply basically the expected return of a call token to be able to sell calls, and vice versa. And depending on the price range they would choose, they would be able to accumulate net exposures in either call or puts. And they could also seek liquidity using options tokens. And this form of LP position is essentially like a closed loan limit. And yeah, so you can visit the math and the app via our website. So look forward to your questions, comments, and feedbacks.
Hello, everybody, again. I figured that after 2 days of heavy formulas, very intricate concepts, unknown to me, I'm going to lighten things up a little bit and bring you down to my IQ level, where I feel comfortable, where my brain, the frequencies at which my brain operates most of the time. So today I'm going to talk about my experience entering the Web3 space via conferences and hackathons. I come from computer science background with web development experience in the industry mostly, working as a technical writer for a year in cybersecurity. So a couple of years ago, 2023, I decided what's going to be a better way to enter the space and explore Web3 than to go boots on the ground and follow the events throughout the globe. So I pulled up the stakes and left attending all the events that I could catch flight connections to in Europe, Southeastern Asia, and yeah, there's 2 places, but they're big. So there are several things that you learn. And the message today, I forgot to mention that, is how should we approach fostering and teaching, growing the new wave of DeFi builders, mostly developers, people coming from the development background. So this is me after winning ETH Global Prize. One of the prize was from CowSwap. Thank you, Felix, wherever you are. And here, obviously, this is me yelling my heart out, trying to win the ledger that was awarded to the one who yelled the most. So I didn't win it, but I lost my voice. So there are 3 main things that I want to say that the devs coming into the Web3 space that need to learn is to handle their keys well. This is really trivial, but very important, because most of I've heard so many stories of devs committing to GitHub repos, leaking them that way, or just mindlessly pasting the code, and then forgetting to set their address on ETH Global site to receive their USDC tokens, and then apparently there are bots that scanning it all the time, and the next transaction goes straight to their wallets. So blockchains are, this is the second message, blockchains are deterministic, and it was very hard for me to wrap my head around this. That's why I think it's very important to explain it to new devs. There are no floating point numbers. There is no randomness. That has to come from oracles. And there are execution costs to everything. So you can, at that time, before LLMs, it was hard to think about coding with efficiency right away. The next things, how much time do I have? Sorry. Okay, so okay, my slides are all over the place, sorry. I wish there was a way to run the slides through LLM before to format it a little bit. But, oh, I'm out of slides, I guess. Sorry, guys. I'm not very experienced, as you could tell, in presenting. But yeah, the main point is that there was a slide about financial concepts. It was very hard for me to learn things like spot prices, derivatives, even in the concept of AMM, because I didn't even know much about order books and how limit orders are structured. So I had to go back and learn how the buyers are matched with sellers to make the trades happen. But to wrap my head around the concept of AMMs, where all the participants and traders and swappers engage directly with the liquidity to make the swaps happen. So whenever you guys chat with developers, please bring that up. Don't think you're patronizing us. We're pretty, yeah, thank you. I'm out of time. Thank you, guys.
Thank you so much. Thanks for staying here for so long, guys. I want to talk about open source and keeping key parts of DeFi decentralized and how we can do so successfully against some pretty strong centralizing forces. We've seen today and yesterday in many presentations that several parts of the trade supply chain in DeFi are strongly centralizing. To no surprise, I think these data points are not new. We see it on the builder side, we see it on the market maker side, we also see it with solvers, with order books, DeFi interfaces, wallets, on all parts. Just a reminder, like if we let this happen too far, the DeFi won't look too different from CeFi, and many of the guarantees that we're hoping to provide to users are threatened, such as permissionlessness or censorship resistance, or efficiency. If you have a monopoly or oligopoly, most likely you will have higher extraction on the users than necessary. And we seem to be taking many of these things for granted, but they really do threaten the promises of DeFi. And we've spent much of our time in the middle as a solver looking into what are the causes of the centralization. And as in most centralization, the causes are some sort of barrier to entry. And there are many types of barrier to entries, mainly trust, brand, network effects, and engineering resources. And it turns out that in solving, the largest barrier to entry is actually interfacing with the DEXs. Theoretically, you could all swap on Uniswap v3 or Uniswap v4. Practically, you cannot. If you're not an engineer and you don't have the time to interface with them, you have to go through some third party to interface with these DEXs. Also, there's a coordination issue in DEXs. If you don't have liquidity, none of the solvers or routers will integrate you. And on the other hand, if you're a router, you will only spend time on the highest priority DEXs. So it's a cold start problem for DEXs, and it also is a cold start problem for becoming a solver or router. And so over time, the participants ossify, and it's really, really hard for new solvers to enter the market. Also, everyone is doing duplicate work. Everyone is doing the same integrations that they really don't want to do. But the one way to break this barrier to entry is to have an open source tool that is credibly neutral in the sense that anybody can contribute. And it lets the DEXs who have the incentive to do so to do the integration themselves once in high quality. And then all solvers have access to the same DEXs and don't need to do any effort, meaning a new solver who wants to enter the market can have the same liquidity as a solver who's been there for 3 years. and can compete on equal terms or roughly equal terms, keeping the market more efficient and decentralized. And you all have one interface to all liquidity in the end. And I want to show like what this has of effect. You can't only just use it for solving. Once you have access to simulating on liquidity, you can do many other things in research, in making DeFi transparent that you couldn't do before. One example is there's many who don't trade in DeFi from TradFi just because AMMs are so unfamiliar. They're not order books. But AMMs are just supply functions. You can cast them into order books. Just do your free simulations, and you can turn them into an order book. But you can't do those simulations if you don't have a way to do that locally. Taiko gives you that. You can now do a simulation on any AMM and build anything on top of that. For example, you could simulate routing over all DEXs and then make an aggregate order book and showcase really what DeFi looks like if cast into an order book. And I want to show you something here. This is built by the community, not by us. Someone actually built this idea. If you go to orderbook.wtf, you can now watch, like this is mainnet, this is live, this is current block. All of we've used to see liquidity aggregated into one global order book. And if you go on any of the simulation points, you can see how it's routed through the different DEXs, at what percentages. You can see all the pools that are coming in. And all of this you can run locally. There's no third party relying on. You can just connect, index, and simulate, and even modify the solver that's behind this. And it's just one example of what you can build on top. This obviously gives like transparency to DeFi that doesn't depend on any third party. But you can also build many other things. So here, if you go to TaikoX on GitHub, every time we get requests, so we get ideas from conferences, we specify out specifications for what you can build, what you can research, what you can turn into open source apps. And if you go there, there's also grants for these. If you want to study on do atomic arbitrage or market making
And
or
that's
arbitrage,
time.
you can do it there.
Thank you.
Hi guys, thanks for being here at this late hour. And so this project will require a bit of out-of-the-box thinking because it's on AMM for energy deep-in. Okay, so this is blockchain for energy. And why blockchain for energy it's interesting? Well, because we are seeing a transformation of the energy market from a top-down, let's say, approach to a bottom-up approach. So before, big generators were being the main provider and giving energy to the grid. And now we have like electric cars, solar panel, battery, maybe in the future, small nuclear reactors, who knows? And is the consumer or the prosumer in this context that supply energy directly. And there are companies like Daylight and Sourceful Energy that have been quite successful in getting money from VCs and are doing blockchain for energy. So what can we bring from the world of DeFi to this world of energy? Well, we can think about bringing AMMs. So let's think about a pool-based AMM energy market. We have a community of prosumers there that are all the households, and they are all connected to the external grid, the orange line, and to a local power station. And we can think this local power station and as having smart meters and being able to interact with a blockchain, which can be a private permissioned blockchain, or it can be even an open blockchain like Ethereum. And the key thing is that a market maker gives posted prices. So if one trades with this tool, there will always be a quoted price for buying price and selling price of the local energy. Now, can we use Uniswap to build this type of market? So in 5 minutes, I don't know how much I will be able to give you the details, but essentially the problem that we are solving is this. So we know that we are in a context where the prosumers can trade with the regular grid, and they can trade internally. So they can trade internally and they can buy the energy at that cost C, and they can sell the energy and get that revenue R. But how do we define this revenue? So how do we even think about designing this? Well, a starting point can be a constant product market maker. Although it will be a bit different from the market makers that we saw until now. So we can think about building prices by keeping constant a product of energy capacity times value of the pool. So we will have energy on the x-axis and the value of the pool on the y-axis. And the slope is the price. So what we do? First of all, we need to bound this price because there has to be no arbitrage with the outside grid. So the price has to be above the selling price to the grid and below the buying price of the grid. This ensures no arbitrage. Then the idea is that, so this will be, I know it's a bit difficult now in a few minutes, but in the paper of the TLDR, there will be all the details. We need to think about this pool as filling and draining the pool. So at every block, the market determines an amount of energy, and this amount of energy determines the intercept on the x-axis of the curve. Then, when all the buyers go and get the energy, we will slide the point on the curve, and the slope of the point will determine the energy price. And there will be batch execution. Then there will be other details to essentially manage when there is an excess supply or a deficit of supply in the community that I don't have time to show you. But the key thing is that this tool, if we start from Uniswap, the price of energy in the local community is the geometric mean of the prices on the grid corrected by some adjustment that induces the supplier to match the demand. So in the paper, so this is a small part of the paper that I'm doing for the TLDR, is with Mateus and Viraj, and there will be this and more. Not only the Uniswap, but how to think about this in general and a simulation of the local grid. Thank you.
Hi, everyone. We've had enough cross-chain, so let's talk about SegTex for a few minutes. My name is Fei. I'm also a fellow this year. This is joint work with Danning, Thomas, and Malesh. And special thanks to a bunch of searchers from Gaussian Process, SEP, Wintermute, and Max for helpful discussions and comments on this work. So a bit of context and motivation. So currently, the Ethereum builder market is dominated by 3 builders. Beaver, Rsync, and Titan, and 2 of them vertically integrated with their own SegTex searcher, and Beaver SCP and Rsync Wintermute. And Titan has exclusive deals with a bunch of other flow providers, including SegTex searchers as well. So the motivation is that economic specifics remain unclear, like what's the arbitrage revenue split between searcher and builder, and do like different searchers have different profitability levels, and how's like what's the impact of exclusive deals like of SegTex flow on builder market, right? So do not have the time to go through the methodology, so I will just like present the results. So we start by identifying SegTex arbitrage transactions using heuristics based on 2 previous papers, but we improve a lot of coverage and accuracy. We'll open source the dataset and the Dune query later. So the results is like we identified about 8.6 million SegTex arbitrage transactions on Ethereum, involving 287 tokens from August 2023 to March 2025. There could be more transactions because like we only consider tokens listed on Binance. Utilizing this dataset, we look at the landscape of the current SegTex arbitrage. So the left panel shows the daily count of SegTex transactions clearly increasing. And the right panel shows like the weekly volume splitted by each searcher. You can pretty much see like some of you may recognize that searcher labels, except FCP and Wintermute are character names from League of Legends. So the landscape is pretty much dominated by SCP and Wintermute, and interestingly, like Kale, the 3rd largest SegTex searcher, was a relatively small searcher before May 2024, and they quickly became the largest SegTex searcher. So we look at the searcher builder integration as well. Like we identify some exclusive patterns between searcher and builder. So the x-axis is the searcher and y-axis is the builder, and the cells shows like how much volume each searcher is sending to each builder. So we identify like several exclusive searchers for that builder, like SCP. Beaver builder have 4, and Titan have 2, and rsync is just window build. Now, so I look at the searcher profitability by integration levels. So this is the bubble plot, like the x-axis shows the median profit margin, and y-axis shows the P&L of the trade, and the bubble size shows the total P&L of the searcher. So we see most exclusive searchers have a lower profit margin and lower median traded P&L than neutral searchers. And if we look into the dynamics between exclusive patterns, so what we see is that like the leftmost panel shows that these searchers trading in their exclusive builder blocks have a higher revenue than in other blocks. And from the middle panel, we show that searchers trade in their exclusive builders block have a lower profit margin than in other blocks. For example, SCP Wintermute send nearly 90% of their arbitrage revenue to their exclusive builder. And as a result, searchers pay much higher payments to their exclusive builder than to other builder. So that basically means like neutral searchers distribute their flow among several builders, but just pay like necessary tips for inclusion and retain a lot of profits themselves. And exclusive searchers direct a lot of profitable trades exclusively to one builder, retain lower profit. But they can probably get near certain inclusion and potential refunds to the builder. And we also show that like to structural shift in the builder market is also like related to the operation of SecTech searchers. The first, don't really have the time. So the first is shows like the rise of Beaver in January, between January to May is like because of the operation of. Okay. Yeah, so don't really have the time. But so yeah, I was just like
I'm sorry, that is time.
yeah, okay. Thank you.
Thank you.
Hi, thanks. So I'm Bo. I'm faculty at Colorado Boulder. Actually, I want to start with a quick plug for academia, the dinosaur in the room. But so I'm in computer science, and our funding's kind of getting crushed right now. And I think it's a big opportunity for the groups in the room because there's going to be a lot of need for funding, or at least hope for funding in academia. And basically, if you can pay to fund a graduate student, then you get them to work on your project and you get a professor to work on the project basically almost for free on top of it. So something to consider. Anyway, I've been working on automated market makers for, 11 years, so about half their life. It's been super exciting to see what they're doing in blockchain. But in the mainstream blockchain, it actually feels very stale and kind of stuck in place compared to where it could be. I think there are people, in the space working on really exciting new automated market maker ideas. But I just want to stimulate your imagination with some ideas that are already out there in the scientific literature and maybe need some collaboration with industry, but could be very possible and I think exciting. So first type is interface. I'll give a couple examples of cool interfaces you can do with an automated market maker. One is, let's say we want to predict a geographical location of something, some event, some object, oil, whatever it is. Just have people pick a point on the map and bet on it, right? People pick a point on the map, bet on it, and as they do, they're producing a heat map of where this thing is likely to be, and you can quote prices for points. This is very easy to do. The mathematics of this is very easy, and I think it's efficient enough to put this on a chain. Another one is we can do an interface on a line. You can have people bet on a Gaussian bump, so they can say, I think the number is going to be around here, and you can offer them a contract that says, all right, if the number's here, your payoff will be this height, the height of the Gaussian, right? If it's here, it'll be this height. And you can quote a price for this Gaussian very easily. And you can like have fixed variance and just have them pick their mean that they want to bet on, pick their height, stuff like that. We know the math of how to do that. Thanks to Alex, who pointed me to a blog post from Paradigm called like distribution markets, where they have a very similar idea. So yeah, there's stuff like that out there. Another one is combinatorial markets. So this is what automated markets were invented to do by Hansen in '03, is to price things like, for example, you have a basketball tournament and you want to quote a price on any one of the 2 to the 64 possible brackets. Okay, or you want to quote a price on something like the event that a certain team makes it to the 4th round, or so on, right? So I'm not just talking about an AMM with like 3 tokens, I'm talking about an AMM with 2 to the 64 tokens. But we have the math for that. Now, this is definitely going to be a challenge on chain. This is going to be a really cool computational challenge. One thing I'll note is you can ask, how much computation can you do off chain, where on chain you just have to verify that like the price is correct. So maybe there's tricks you can do. And then the last one I want to talk about is algorithms. So sometimes feels like in automated market makers and blockchain, constant product fell out of the sky and hit us on the head. And like we're still lying on the ground recovering from that. But there's more. There's other things you could do. So for example, one thing that maybe we all thought we wanted to do was look at the history of prices over time, run a machine learning algorithm based on the past, and use that to predict the best price in the future. Okay, and then we realized that was a really dumb thing to do. But you know who does that? Uniswap. Okay, so it turns out you can take any constant function market maker and interpret it as a machine learning algorithm, which you take the past history of prices, and that determines the current price that you're offering. And if you're in a high liquidity environment, the price roughly looks like this. It's almost flat, or the bonding curve is almost flat. And if you just charge that price, you would be just moving along this straight line. So as we know, we have to charge a little curvature fee. And so one thing that one of my recent papers looks at is, let's use a different machine learning algorithm, charge that price, and add a little curvature fee. And you're still going to get all of the properties that you want from constant product. So there's a lot of cool things you can do. Please investigate them. I'd love to talk about them. Thank you.
I'm Anthony Hart. I'm a researcher at Heliax, and I'm here to talk to you about data structures. The theme of this talk is that trees are bad. What do I mean by trees? I mean trees as a data structure, specifically abstract syntax trees. Historically, there are a lot of things that we want to consider, which we've turned into trees even though they really aren't. Most of them become abstract binding trees. So some common examples include lambda expressions, let expressions, quantifiers, and integrals. These are trees that bind variables so that leaves can connect to each other through shared variable references. They're basically trees that wish they were graphs. This leads to a bunch of nominal issues, specifically fresh names. You need an infinite set of variables as part of your syntax, shadowing, alpha equivalence. Some systems have an issue I call pegging. So in classical first order logic, you can translate a formula to pre-next normal form, which moves all the quantifiers to the front. And what this implies is that the exact position of the quantifiers within a formula is encoding essentially random information that the semantics doesn't actually care about. Some systems have an issue of pointless scoping. So in the pure lambda calculus, it's just a rewrite system. There's no actual need for variable scoping, but it's always scoped anyway. Traditional solutions to this problem have tried to stick with trees, and these lead to combinator systems. There have been a couple historically. There's traditional combinators. There's Quine has its own system, and there's relation algebra. These require an awkward yoga of point-free combinators, and they spend most of their effort essentially trying to get different distant parts of a tree to communicate with each other, and it completely scrambles the original expression. Additionally, trees encourage resource-insensitive rewrites. So these are two very basic rewrites. The first one copies x, which can be arbitrarily large. The second one deletes y, which can also be arbitrarily large. You can make these finite and resource aware, but it's really awkward. So what's the solution? Is it graphs? The answer is no, because graphs are not a generalization of trees. Graphs cannot distinguish between bxy and byx. Those two graphs are isomorphic. Also, graphs have an additional problem that isomorphism is not known to be efficient for graphs. The actual solution is string diagrams, which are graphs such that each node defines an ordering on their edges. These are a generalization of trees, and isomorphism checking is efficient for them. With them, so in this example, I'm translating a lambda expression into a kind of string diagram. Those labels are not actually part of the data structure. They're there for understanding. So this allows us to completely factor out the need for names without scrambling the expression. When you do graph rewrite rules, they naturally want to be local and finite. So here's the analogs for duplication and deletion. And as you can see, they do deletion and duplication piecemeal rather than being highly non-local. Trying to make them non-local and infinite would actually be much more difficult when you're dealing with graphs. Rewrites can be applied in parallel and in any order. That's concurrency. So you can treat this rewrite system as a concurrent model of computation. And if the system happens to be confluent, which is often easy to engineer in practice, then there aren't any race conditions, which is pretty nice. Programs are conceptually similar to pure functional programs. And I'm looking into them for certain kinds of generalized intent solving. It might be useful for other kinds of distributed computations. Histories of these rewrites become these higher dimensional generalizations called surface diagrams, and they are actually encoded in a way that's very similar to the two-dimensional diagrams. Each step of computation adds an additional node to this hypergraph, and this allows arithmetization of histories to be efficient for the same reason that many ZKVM arithmetizations are efficient. For example, TinyRAM. The width of a Plonkish arithmetization matrix is proportional to the encoding of a single node. That's specifically because of that local rewrite property. There are lots of different string diagram languages for many different applications: quantum mechanics, electrical circuits, physical systems, game theory, full first order logic, and all of these could be turned into bespoke ZKVMs if you wanted to. And as a final thing, trees also make induction more difficult than it need to be. Induction isn't predicative because it quantifies over predicates. Alternatively, you need infinite axioms to an axiom scheme. If you replace tree proofs with cyclic proofs that are graphs that satisfy a cycle constraint, then you can get the power of induction without needing infinite axioms or impredicativity. Also, regular expressions only have a finite basis if you use string diagrams as syntax. They do not have a finite basis if you use trees. And so these graphs are strictly more expressive than trees. And that's it.
Thank you, and let's give one more round of applause for all 12 of the Lightning Talk speakers.